All right, ladies and gentlemen, good morning, good afternoon, good evening to you, wherever you may be. Thank you for joining us today for KEMET's webinar on choosing passive components for your DC to DC converter. My name is David Adib. I am a Senior Technical Marketing Engineer here with KEMET in Florida, and I will be your webinar host for this session. During the session, I encourage you to ask questions using the Q&A functionality in Zoom. And I would ask you not to choose the, or not to use the chat functionality, just use the Q&A functionality instead. I encourage you to ask questions, ask as many questions as you'd like. Your questions would be, generally speaking, answered at the end of the webinar. And we will try to answer as many questions as time permits. With that said, I'll turn it over to Wilmer. And hello, Wilmer. Thank you for presenting this, and please introduce yourself, and you can go ahead and start with your presentation.
Excellent. Thank you, David. And yes, my name is Wilmer Companioni, and welcome to this, our latest session in KEMET's Global Webinar Series. Today, we'll be discussing choosing the right passive components for your DC to DC converter. And choosing those components is a careful balance of different trade-offs and pros and cons from all the options in front of you. So we'll get into what some of those pros and cons and trade-offs are a little later into the presentation. So as I said, I'm obviously Wilmer Companioni, and the guy in the picture was fresh off of a shave and a haircut. Right now, I'm 60+ days since, but I promise that is me. I have a BSEE from the University of Florida and 14 years of industry experience with 6 years in marketing. Now, I know the numbers on that slide don't exactly add up to 14. That's because there was some overlap between some stages in this journey. So today's agenda, we'll start off by covering some DC to DC converter basics, just to bring us all to the same baseline. Then we'll be showing how the inductance is determined, and then the different inductor choices that you have in front of you. And then a similar process with capacitance, how that capacitance is determined, and then the trade-offs between the different choices of capacitor technologies. We'll also be getting into some of the simulation tools to aid in this design effort, which can be very helpful in speeding up the design cycles. We'll close with some key takeaways, and then we'll open it to Q&A. As David said, the Q&A, please use the Q&A portion of the Zoom window so that we have a clear documented list of all the questions that are asked, and to not use the chat portion of the Zoom window. So what is a DC to DC converter? It's a type of switching regulator that takes in one type of DC voltage and converts it to another type of DC voltage. Now, the purpose of a regulator is to take in that input voltage that may have some variation to it and maintain a stable output voltage. That output voltage can be either stepped up, sometimes called boost, or stepped down, sometimes called a buck. And in addition to creating that output voltage, a good regulator must also maintain stable output voltage when the load amount, the load current changes. Now, the regulator is allowed a moment of adjusting to that load, but a good regulator minimizes the settling time and the related overshoot and undershoot of that change in load. And this is what is the so-called transient response of a regulator. Now, these regulators come in many different topologies. This is not the exclusive and only list of different regulator topologies, but those different topologies work in careful concert with the passive elements that are related to them. A buck converter produces output voltage that is less than the input voltage, and it also has output current that is more than the input current. A boost converter does the inverse of that. The output voltage is greater than the input voltage, but that output current is also less than the input current. And that is because we are all slaves to the first law of thermodynamics that says energy must always be conserved. So the power in must always be equal to the power out of one of these types of circuits. Now, inductors control the current by way of creating and collapsing a magnetic field, and capacitors control the output voltage by storing energy and filtering that output voltage. So let's do a quick poll question here, and I'll launch this poll. Is what type of regulator do you use most often? So we'll spend just a few seconds here trying to get some inputs to what this poll question is, and we'll share the results of this polling in the follow-up email to this webinar. So I'll end the polling now, and we'll move on. So determining the inductance is specified by the operating conditions of the regulator. So these are just some of the operating parameters that are pertinent to a DC to DC converter. Now, determining that inductance is a fairly simple calculation, and it takes into account the input voltage, the output voltage, the ripple current, the switching frequency, et cetera, et cetera. Now, the actual derivation of this equation is a topic for another day, but after plugging in our operating conditions, we come up with a value of 40.44 microhenries. And just that value alone is not enough to actually build this design. There are many different options to consider. First of all, 40.44 is not an actual inductor value. We have to choose whether to go up to 47 microhenries or down to 33 microhenries from there. That would cause a change in the amount of output ripple current. And there's also the question of what inductor material to use. Is it a ferrite type inductor or a metal composite inductor? And that's one of the things that we'll be exploring next. What happens with those different material options? So there is no one size fits all inductor. That doesn't exist. There isn't a perfect inductor that will work optimally under all conditions. Each of them goes through their pros and cons. So for example, a metal composite inductor has a soft saturation profile, a fairly high saturation current, and is very temperature stable. Now, some of the cons of that is that they're somewhat limited in the relative amount of inductance, and they are somewhat larger in size than some of their ferrite counterparts that have high permeability, come in generally small sizes, and are somewhat stable below saturation. Their inductance is stable below that saturation current. But they come with the drawback that there is temperature variation, and they have what's called a hard saturation profile. If you look at the graph at the top of the chart here, at the top of the slide, the inductance versus current of one of these ferrite inductors falls off pretty sharply once you hit that saturation point. And that's not necessarily the case with metal composite inductors. And of course, why does this matter? That matters because loads are not always constant. Loads can vary. So any change in that output current, when you're operating in that hard saturation profile of an inductor, can actually have an impact on the amount of actual delivered inductance. And that variation can deviate pretty far away from your target inductance. And that deviation will take you away from your desired operating parameters. Whereas if you were to choose an inductor, a metal composite inductor with a softer saturation profile, where the current is much more stable with, where the inductance is much more stable with output current, then that softer saturation profile will not, or will have much less of an effect on the actual delivered inductance, and that'll help maintain you closer to the desired operating conditions. And inductors are known to heat up during their operation for several reasons. The power loss, and therefore the ultimate heating, the amount of heating, self-heating that that inductor experiences, is determined by the DC power loss, and that comes from the resistivity of copper, the AC power loss that comes from the impedance of the winding, and the magnetic losses in the core material itself. Then when you multiply that total power loss times the coefficient of thermal resistance of the component itself, you can get a sense of the total temperature change of the inductor itself. And using our simulation tool, KSIM, you can get a sense of how much expected heating an inductor can experience under those particular conditions. And if you follow the link there, it'll take you to this specific project where we're comparing two different inductors and how much they heat up. And we also have a YouTube video that you can follow through that link there that shows you this effect. So the dominant losses in an inductor have a dependency on the amount of output current. So in low current conditions, lower current conditions, the core loss is the dominant loss mechanism. But as you increase in current, then the copper loss begins to be more and more significant as a loss mechanism. So let's take a closer look at core loss. The amount of that core loss is determined by the core material itself. And while ferrite inductors have a limitation in their amount of current, as I mentioned earlier, as you go higher and higher in current on these ferrite types of inductors, you can hit that hard saturation fall off. Those ferrite inductors also have lower core loss than their metal composite counterparts. So again, just another information as far as which trade-offs to consider. So as I said, there's a lot to consider on just the inductor alone. Plugging in the operating parameters into that inductance equation I introduced earlier is not the only part of engineering. Knowing and balancing those trade-offs between the different choices you have available is another important part. And it's the application itself that will determine what materials and what choices to go after. And this table here is not to be thought of as the inductor Bible, and this is the end all be all as far as your inductor decisions go. It's supposed to serve as a guide. But in general, when you select whatever your more important constraints are, that is what should go on to determine what particular inductor technology you use. But then keep in mind that you may be trading off some other things. So let's say size is, or let's say current is one of your more important design constraints. You need to operate on those higher current conditions. That would drive your decision toward a metal composite option, but you have to keep in mind that you're sacrificing things like total inductance, the size, the frequency, the DC resistance, and perhaps somewhat importantly, also the price. Just taking a quick glance at all the different prices of all these different options, generally, not always, but generally the ferrite types tend to be a little bit on the less expensive side than the metal composite counterparts. So another poll question: what type of inductor are you most familiar with? So let's launch the poll here and give ourselves a little bit of time to answer this question. Okay, getting some interesting results here. Okay, we'll end the polling now. Thank you for everybody that participated in the poll. So let's move on to the capacitor. The inductor is just one of the choices that must be made when and selecting a capacitor isn't necessarily any simpler. I know many times inductors and those things in the magnetics realm can somewhat appear to be a little bit of black magic, and it is, and selecting an inductor is by no means a trivial task, but capacitors are no simpler, or no easier. There's a lot to be considered. Those very same operating parameters are what should determine your capacitance value. And when you plug those into those operating conditions into the equations, the formulas that determine your minimum output capacitance and your maximum output ESR, for this particular example, we end up at a conclusion that we need 30.8 microfarads with a maximum ESR of 20 milliohms. So just as with the inductors, there's many different options available to hit these conditions. Each of those come with their pros and cons. And these choices have significant impacts to the resultant output of the regulator itself. So the output ripple voltage is affected by many capacitor factors. So at the top of the chart, we have what is a somewhat ideal or close to ideal at the output ripple voltage. And that ripple voltage will always be there as a function of that switching element of this regulator. And then as we start to introduce an effect such as ESR, we see that impacts an MLCC and X5R choice a bit differently than how it impacts a polymer capacitor choice. And as we start to take into account more effects, such as the effective series inductance, the DC bias effect that comes into play with class 2 ceramic capacitors, and finally, the so-called cap roll-off related with polymer capacitors, these parasitic effects of the inductor choice have a large impact on the output ripple voltage. These are what are some of the things to consider when trying to select an output capacitor. So we have actually done this experiment, and we have again a video on YouTube that shows how the output ripple is affected by the different capacitor choices. And this is not to say that there is a perfect choice. Like I said earlier, it should be the specific design constraints and requirements that drive you to selecting one option or another. So let's go over this. These are just 3 types of capacitors that can fit our particular design that we outlined before. So we have an X7R 1210 option that has very low ESR. X7R operates at a very wide temperature range. And in order to hit that required capacitance, we needed multiple placements of this component. But the end result was actually a fairly low ripple voltage of 1.5 millivolts or so. In an X5R condition, X5Rs have a little bit more capacitance than X7Rs, and it's small size, a single placement, but then that comes in with the effect that it's not as temperature stable as its X7R counterpart, and it results in a 4.6 millivolt output voltage. And then finally, the case of our tantalum polymer capacitors. So those have very high volumetric efficiency. They are voltage stable and have can cram a lot of capacitance into a small space, but they have relatively higher ESR, and we end up with an output voltage ripple of 30.7 millivolts. And using a tool like KSIM, which is available at ksim3.kemet.com, or following this project link here specifically, you can estimate the amount of ESR among these three different options. And when it comes to class 2 ceramic capacitors, we've all heard of the derating of ceramic capacitors, and that's because these class 2 ceramic capacitors, because of the nature of the material itself, they lose capacitance with applied bias voltage. And we don't have to get into the exact physics and mechanisms of that, but suffice to say that we offer a tool like KSIM to help you try to estimate that effect. So then your supposed 22 microfarad capacitor under conditions may not be 22 microfarads at the end of the day. So much like an inductor, capacitors also have a self-heating result to them. They also dissipate power. And it's a function of the output current and the ESR. So an equation that we're all very familiar with, that I²R calculation. So the square of the output current multiplied by the ESR is the total amount of power dissipated, and then once again multiplying that by the coefficient of thermal resistance is the resultant self-heating of the capacitive element in this case. And that is also something that can be estimated using our design tool KSIM that you can explore by following the link on that project there. So let's get to some capacitor conclusions. Arriving at the target capacitance using those equations I mentioned earlier is only the beginning. And arriving at that target capacitance can be accomplished using several different capacitor options, each with their trade-offs. And in some ways, determining the right capacitance technology can be more daunting than the inductor technology. And these are just 3 of our top capacitor options. And furthermore, the magnitude of the trade-off is related to the magnitude of how important the constraints are. So at first glance, it might seem like ceramic capacitors are the optimal choice, and very often they are, but there are design constraints that may drive you to other options. For example, if the space design constraint is sufficient enough that that a ceramic or multiple placement of ceramic capacitors is just not going to fit, then that might drive you in favor of a tantalum polymer capacitor that has much higher, as we call it, volumetric efficiency. But you have to keep in mind that you may be sacrificing voltage or frequency or temperature when you go with that option. Ultimately, I can't give you all the answers here. I want to arm you with some of the knowledge of what these trade-offs might be. And of course, there looks like there's a little bit of overlap here between some of the constraints and the trade-offs, and that's because, as I said earlier, how important that trade-off is what's going to drive you to choosing one type of technology or another. So I think this is our final poll question of the day. What is your preferred type of capacitor? Let me launch this poll question, and we'll give ourselves a little bit of time to answer this question. So what is your preferred type of capacitor? Ceramic, tantalum polymer, aluminum electrolytic, or the one with all the farads? Okay, so we'll end the polling here. Thank you very much to everybody that participated in this poll. So now we'll open it up to questions. As we said earlier, please submit your questions through the Q&A window of the Zoom, and we'll try to answer as many as we can. I believe we have about 30 minutes, so we can get to a lot of questions. And yes, sir.
Yes, sorry, Wilmer. Yeah, we actually have received 2 questions so far. If you'd like, we can start by answering those.
Yeah, let's give it a go.
Okay, so the first question from an anonymous attendee, and he or she says, when you choose your capacitor, how can you determine its power losses, and between parentheses, for high voltage and current application?
Well, how can you determine its power losses for high voltage and current applications? Well, there's several ways you can do that. As I said earlier, we have something like this, our tool KSIM that you can find on ksim3.kemet.com, that if you were to select your capacitor and apply those specific conditions to it, then you can change to this chart here that will tell you the temperature rise with the amount of current. And the way this works is that it applies that current with the specific ESR at a known frequency, and that estimates the total power dissipation. The tool also knows the coefficient of thermal resistance of the component itself, and from that, you can estimate the total amount of temperature rise. So for a capacitor in particular, the power loss is determined by 2 things. The output current, in the case of a switching regulator, the output current, and the ESR of the capacitor.
Okay. And then moving on to the second question from Elena. Thank you for sending us your question. The question says, do you have ESL plots for different packages for MLCC? And then, yeah, the 603 and 805, 1206, and the 1210 series.
Yes, we do. I don't have that. I don't have that slide selected here, or that plot selected here. But let's see. Going back to KSIM again, we have several different plot types available, including impedance and ESR that you can see here, as well as capacitance and inductance. And from when you switch to that capacitance and inductance plot, you can see the estimated amount of ESL. And also the ESL is what determines, one of the things that determine this point of self-resonance. So if you were to select, 3 capacitors of different sizes, but the same capacitance value, this self-resonant point will be different for all 3 because they have differing ESLs. And that self-resonant point, very quickly, is the point at which the capacitive reactance is equal to the inductive reactance, and those 2 elements cancel out in the impedance equation, and all you're left with is the real portion, the resistive portion of the ESR curve or the impedance curve.
Okay. And speaking of which, I'd like to remind our attendees that don't forget to join us on Wednesday of this week. You will be given a virtual tour of KEMET's new digital experience, in which you'll actually learn a lot more about KEMET's digital tools that will help you with your design. Most of all, the new KEMET website and the KSIM tool that you have learned of during this webinar. Our next question is from Paul. Thank you, Paul, for sending us your question. And his question says, can you say a few words about the aging effects on metal composite inductors, usually relates to organic binding agents?
Aging effects of metal composite inductors. I am familiar with the organic binders that are used in those metal composite inductors. I have to say, I'm not familiar with aging effects on that binding material. So that's maybe something I'll get back to you, David. Please make a note of Paul's contact information so that we can go back and answer that question. But I guess for those that may not be familiar with the actual mechanics of construction of a metal composite inductor, it starts off as metal powder that is compressed along with an organic binder into that shape, and it is not a sintering process. A sintering is when those powders, those particles are allowed to grow together. They're actually, those particles are in a metal composite inductor are actually isolated from one another using this binder and isolating material. And that's similar to, the reason for that is similar to why we have laminations in transformers, is to minimize some of those losses due to eddy currents and things like that. But as far as an aging effect to them, that may be something I have to go back and research a bit.
Okay, and I've made a note of it, so we'll get back to Paul on that. And the good news is we've had quite a few questions coming in, which is very good. So our next question is from Kenneth, and Kenneth says, power in a capacitor equals I squared times ESR. Can you explain, is all the current passing through the capacitor?
Yeah, that's a sort of interesting kind of philosophical question. I've had similar discussions many times with people. You know, you get into the philosophies of capacitance, right? Does current actually pass through a capacitor? And I mean, to get down into somewhat what the physics are is, you have the buildup of an electrostatic field between the two plates of a capacitor, and as that electrostatic field dissipates, you have this I don't know, let's say evolved current out of the capacitor. So it's not that I wouldn't say it's passing through or that the electrons are passing through, but there is a buildup of charge that as you were to discharge that field and the capacitor, the charge on top of the capacitor itself goes out, then that is necessarily results in a current. So it's not so much that it's passing through like a fluid or something like that, but it's the building up and collapsing of that electrostatic field that results in that necessarily has to result in a current. But that current causes losses because of the losses in the dielectric itself, the ESR, and then why the ESR is there. There's a component because of the losses in the dielectric, and component because of the losses in the electrode structure itself, as well as losses in the termination material. So there's, much like an inductor has different reasons for their losses, so does a capacitor.
Okay. Yeah, it's one of those questions that seem at first easy to answer, and yet they're not so easy. Then our next question comes from Prem Kumar, and Prem says, what will the effect of mounting aluminum electrolytic capacitors upside down for a long time?
Aluminum electrolytic capacitors
upside down for a long time. What would the effect be?
I'm not familiar with an effect. I mean, I might be. It's an interesting question. I'm not an expert on upside down mounted aluminum electrolytic capacitors. I don't know of any effect because the electrolyte is not in liquid form. I know we sort of tend to think of electrolyte and these things as like filled with a liquid. Ultimately, the electrolyte itself is actually suspended in a paper medium, a very porous, highly porous paper medium that essentially holds the electrolyte in place. And an effect, if any, that I may think of is some of the larger aluminum electrolytic cans have safety vents on the top. And if you were to mount it upside down for a long period of time, it may, the amount of built up pressure might actually increase before that safety vent is triggered, because those evolved gases are trying to find a different path out. But that's a very unique condition. I'm not sure I've come across it.
Okay. And we actually have yet another question from Paul. Are the KSIM results typical? If typical, then how much variation might exist for a population of parts with a KSIM result?
So yeah, the best way to answer that is how we get these KSIM plots. These KSIM plots are actually based on measured data. So we have, let's call it, some characteristic equations that that give the shape to these plots and curves as they appear on the screen. And those equations have coefficients and related constants that ultimately change the shape of these curves. So we take measured data and we change those coefficients until the simulated curve, the modeled curve, lines up right on top of the measured data, and then we save it that way. So it's the KSIM data is based on both measured and actual results. And one of the ways that we try to account for some slight variations in the population is that measured data is the average of a population of five of the components. It changes slightly from type to type, but we measure more than just one, sum them up, and average that out. So we try to get a more typical response that takes into account those slight variations.
Okay. All right, moving on. Our next question is from Mark. And the question says, what applications drive the metal composite inductor market development?
Ooh, metal composite.
That's a good question.
Inductor market development. Yeah. It depends. Those high power, high current applications, those will be those cases. Anytime that you're driving, I mean, really just kind of a rule of thumb, 10 or more amps or so using one of these DC to DC regulators, you'll generally be toward the metal composite power inductor side. Now that could be used in power supplies for many different things. It could be used for wireless charging systems. It could be used for infrastructure, telecom infrastructure. Automotive is another option where these metal composite power inductors are finding space, finding room, especially in that one in particular. Metal composite inductors are the preferred choice because of their temperature stability. With ferrites, you can get, as I said, more inductance, but they start to deviate as you increase in temperature, more so than a metal composite inductor option.
Okay. And our next question is from an anonymous participant, and the question says, I guess he's referring to his earlier question. So the question was, do you have ESL by package type? I don't want to have to calculate it by going back from the KSIM result and removing the capacitance.
Yeah, ESL by package type. It's a little bit hard to, yes, the package type does have an impact on ESL, especially as the size of the terminations on the capacitor is a component to the ESL. It'll be hard to say that we have anything that just goes 1206, this is the ESL, 0603, this is the ESL, because the actual layer count and structure of how these multi-layer ceramic capacitor options are built up also have an impact into the ESL. So I think there's too much that goes into what gives rise to ESL to maybe summarize it as just this is the package, this is the ESL. I think for a given cap value, we can start to get to that sense, but across the board, that's a more difficult exercise. I could go back and ask that question of our ceramics team and see if we can come to something a little bit more concise than that. But off the top of my head, I don't think we have anything like that.
Okay. And Michael also sent us a question, so thank you, Michael, for that. And the question says, is temperature rise the only limiting factor for how much ripple current an MLCC can handle? Does the temperature rise estimate assume a certain amount of copper area on the PCB?
That is a good question. Yeah, so ultimately, the more heatsink you have, the more temperature you can drive essentially with these capacitors. So you know, really big, thick copper traces attached to this to these components obviously will sink a lot of heat out of that device. So that is a factor that must be considered. And I forget exactly off the top of my head what those particular conditions are that we use in the case in simulation. We can try to get back to you on that. But yeah, if you were to use you know, 1/4 ounce copper, you're gonna get a lot more temperature rise than if you use like some really heavy, like 2 ounce copper or something like that, right? Because you have much more place for that heat to go through. So these specific mounting options do have an impact on temperature rise. We actually also have some of our stacking technologies that you can place ceramic capacitors not in the sort of pancake stacked orientation you would think of. You can actually mount them on their side where each individual capacitor is perpendicular to the board. And that also has an impact on how much heat is dissipated. It makes for a better radiator that way. So yes, mounting options are a big consideration in estimating the amount of temperature rise. Okay.
And Wilmer, we do have a few more minutes for a few more questions.
Okay, yeah, let's do it.
Okay, yeah, because they keep coming in, so we have about another 5 or 6 questions yet to go.
I'm committed to an hour of this, and thank you everybody for committing to an hour of this, and we'll stay on as long as we have to.
All right, sounds good. So let's move on to our next question. It's actually a follow-up question from Kenneth, who asked us about the power in a capacitor, the I squared times ESR. So his follow-up question, wouldn't it be delta I? And I believe he's referring to when he says is all the current passing through the capacitor.
Oh, delta
It's the I squared ESR question.
Delta I. Yes, it would be. Yes, it will be. So
okay.
It's simple enough. Yeah, good catch.
Okay. And Prem Kumar sent us yet another question. Thank you for your participation. Can you explain on inductor versus switching frequency?
Okay, inductor versus switching frequency. So that sort of comes into play. Let me get to this slide here. Where was that thing? Okay, so this is an example of switching frequency. So the amount of switching frequency also impacts the amount of core loss when considering the two different types of inductors, metal composite and ferrite inductors. So ferrite inductors, as I mentioned, have generally lower lower core loss than its metal composite counterparts, especially as it pertains to the switching frequency. In the case of metal composite inductors, their core loss starts to go down as you increase in frequency. And in the case of ferrites, it starts off fairly low and somewhat stabilizes. Ultimately, in the case of metal composite inductors, you get to a point where your switching frequency is so high that it essentially is unseen by the metal composite inductor. But anyway, yeah, these are some of the effects of switching frequency. Is it can impact, depending on which type you choose, the amount of core loss.
Okay. And our next question is from Ken. And what is the plan for sending out slides or link to the recorded webinar? And we will actually do that. I can easily answer that question. So yes, you will get, we will actually publish the slides of the webinar, as well as the recording that you can go back to and look at the slides once again and or listen to the recording if you would like. Do you want to add anything to that, Wilmer?
No, that's it.
Okay.
In the next day or so, everybody that attended this webinar, well, everybody that registered for this webinar will get a follow-up email, obviously thanking you for attending, with a link to where we can get these slides. In addition to that, we will post the recording of this slide and the presentation itself on our Engineering Center page. I believe it's ec.kemet.com/events/webinars.
And Kenneth sent you a thank you note. It says, good explanation about capacitor ESL. Thanks. So thank you, Kenneth. I appreciate that and appreciate you joining us today. Our next question is somewhat of a lengthy question. I'm not sure if there is a way I can simply send you the question in the tool here.
I feel it's lengthy. Let's maybe follow up offline so that we can.
Okay. All right. The next one is not as lengthy. It may be a little easier to answer. Jay sent us a message saying, hi, I joined this webinar 8 minutes late. Well, we're glad you joined, Jay, anyway. So I might have missed out some part regarding inductors, but I had a couple of questions. How are the winding losses of inductor accounted for during the design process of DCDC converters? Okay. There's other parts to this question, but we'll take it one at a time first.
So we'll let's just very quickly take a look at the losses here. So there's three mechanisms of loss in a power inductor. It's the DC loss that comes up as a result of the resistivity of copper. There's the AC loss that comes up as a result of the impedance of the windings. And then there's the core loss. Collectively, the DC and AC losses can be thought of as the copper losses. And then the core loss is kind of a separate effect that I mentioned earlier. And as you increase in current, the dominant loss mechanism changes from being primarily driven by the core to being primarily driven by the copper loss, so that AC loss and that DC loss.
Okay. And the second part of his question says, how is the loss distribution among the components? I think we have already answered that. Is it switching losses or winding power losses from magnetics dominant at full load operations?
Yeah, I think that's kind of covered here. One of the things I want to make mention is that we've recently introduced the inductor tool into KSIM, right? The ability to estimate the effects and the electrical performance of inductors in KSIM. And one of the changes that we would like to make here very quickly is to split up those losses. Right now, the losses that we have shown here, where are they? I showed that earlier. Here, right now, the losses that we have shown here are the combined losses. But I'll take that comment and similar comments that I've received before, that we should split up those losses so that users can get a sense of what's the dominant factor of the losses. So look forward to that on our KSIM tool.
Okay. And finally, just a comment from our anonymous attendee. It says, great presentation, thanks. So thank you for joining us, and we're glad that you were here. With that said, these are all the questions that we've received. So anything else you want to add, Wilmer, before we close?
Let me quickly advance here to my last slide where we're teasing. Just quickly teasing some of the upcoming webinars that we have. As David mentioned, Wednesday of this week, we'll be going through an overview of our revamped and re-envisioned and the future of our digital experience. David will be taking us through KSIM 3.0, the new KEMET.com. If you haven't seen it, please check it out. And a few other new digital tools that we've introduced to make the lives of designers easier. And that's this Wednesday, 2 days from today. Now, Monday of next week, we'll cover the detail and applications of PIR sensors. Wednesday, we will cover lifetime calculations. And then finally on Friday, we'll have a webinar in Mandarin language, why Polymer is better than MnO2. So if you haven't done so, please register for one of those three. We have a great lineup of events coming up. And thank you very much. If you have any other questions, you can submit them through the contact us. And David and I obviously have some follow-up to do with some of these questions that came in.
Well, there was one other question that came in. Since we have a few minutes, you want to close out with that?
Let's do it.
Okay. Does KSIM allow for adding tolerance numbers?
Yes. That's you can add the tolerance to KSIM, and we've kicked around the idea of adding tolerance bands to the different plots that you see on KSIM. One of the reasons why we didn't introduce it yet is that it became a bit of a cumbersome UI experience trying to show that succinctly for the different types of plots. So you can, so ultimately shortening the answer, yes, you can select your tolerance in KSIM, but I know that there's better ways to show that, and we'll try to get some of those in as we go on to improve our tools and our overall digital experience as a whole.
And Wilmer, will we be doing any webinars on EMC components, common mode filter and differential mode filter?
Yes, actually, next month, the month of June, is a month where we're going to start to sort of go back to basics a little bit. So our whole webinar series will be one that we go back to basics of components and leading into basics of applications and how they're used. And that's a topic that we have on the docket.
Okay. And with that said, that concludes all the questions that we've received so far. Wilmer, unless you have anything else to say, I wanted to thank everybody that attended with us and that participated with questions or poll questions. And Wilmer, you have any closing remarks?
No, that's it. Thank you everybody for attending, and I hope to see you at a future KEMET webinar.
And thank you, Wilmer, for a great presentation. Thanks to everyone. Appreciate it. Have a great day.
Bye.
Thanks.